I'm Greg Benedis-Grab. I primarily work at a school in Brooklyn. It's an independent school, but I'm also really into programming. I'm really excited about creative coding, and at the school where I work and also with other teachers, I do a lot of work kind of collaborating with teachers, and I also do some workshops with the group STEM Teachers NYC. And so what I'm trying to do here is talk about this idea that I have around creative coding for STEAM. So I'm going to spend a little bit of time talking about what I mean by that, kind of giving some context, but I think what's really exciting about it is seeing the possibilities. So I'm going to share about 3 sketches with you that I've used in collaborating with teachers and show you why I'm so excited about this idea. And feel free to stop me at any time. I like to have like an interactive style, so if you have any questions or thoughts, just let me know. Okay, so let's start by talking a little bit about computing. My background is originally in science education, and so one of the things that excites me about computing is for a really long time in the history of science, there were kind of 2 types of science. There was experimental science, and there was theoretical science. And then computers were invented, and now there's computational science. And in fact, computational science has become equally important to those other 2 areas. And it's sort of had an amazing effect on all areas of science. I mean, much bigger than science. I'm really excited about science and those kinds of things, so that's why I called it kind of creative coding for STEAM, but I think it even goes beyond that as we start to talk about it. And in some fields, it's been really transformative. Like you think about the sequencing of the genome. In some ways, computational biology is just the new biology. And you know, so it's had like huge effects, things like fluid dynamics. You can now track things that were almost impossible to make sense of before computers. I think in some areas the path has not been as straightforward. Like in the 80s, there was sort of this sense that artificial intelligence was close to being figured out. That didn't really happen exactly the way they had anticipated, and yet I think computers are making us think about a lot of different things. So I think computing is really an exciting and important part of STEM. And I put the A in there because I'm excited about the arts, and I'll get to that in a little bit. But I think it's important to think about the fact that computing is just a big part of the world that we live in. So the next kind of thing, is my voice good enough when I'm up here?
Yeah, we can hear you.
What?
I'm at the back and I can hear you.
You can hear me? Is it good for the camera? I hope. Hopefully everything works out.
Yeah,
I just don't like standing behind a podium that much. So I wanted to talk a little bit about the history of computing and education. Also, that's sort of a context for what I was thinking about. Computers have really been a part of education since they were first created. In the 80s, this was the computer that I had. I didn't have the fancy monitor. My parents just got this really cheap black and white, but you could like connect to channel 3 and see all this stuff on the Commodore. I love the Commodore 64. But from the very beginning, there was this sense that computers were going to play an important part in education. And I think in the 60s, there was this idea of computer-aided instruction. So you can bring in tech into the classroom, and it's going to transform things. And to be honest, most of the ed tech world is still in the 60s. That's sort of how a lot of people think about technology, like it's this add-on that's in the classroom that you kind of use it, you bring in media, you bring in different things. Later in the 70s, there was this sense of the cognitive tutor, and you see this now in some testing software, like it'll be responsive to the student, and it's using, especially with some of the machine learning techniques, it's trying to kind of be responsive to the learner. Then maybe like in the 80s, there was more of a focus on like maybe this computer science should be a subject in school and learning about programming. So what I'm saying is offering here is a kind of a different perspective on it, which I'm calling CCSTEAM. And let me just give you a sense of what I'm talking about here. So I'm thinking of, when I talk about creative coding for STEAM, I'm kind of thinking of three different things. One is kind of computing literacy, and I kind of am concerned about that word because often when you talk about computing literacy or technical literacy, people go to these very basic ideas like knowing how to turn on a computer or knowing how to like copy and paste something from two Microsoft applications. And I think we've sort of lost sight of what literacy is really about. And I draw on this from some of the work from Andrea de Sessa. He had some really interesting ideas about like literacy is really a cognitive tool. So if you think of all the, and he first talks a little bit about textual literacy, and being able to interact with texts is something that extends the power of your brain. Like without these books, without this literature, without this kind of set of skills that we use around textual literacy, we wouldn't be able to do as much intellectually or artistically or in all the ways that we do things. And I think computing is another form of literacy. It's like something that allows you to extend what's possible with the limitations of your brain. And so I want students to kind of tap into that. And so kind of in contrast to this computer-aided instruction where somebody just creates something for you and then you see it in the classroom, students can be using these tools to advance their thinking, to advance the way that they're learning. The second thing I think about with the creative coding for STEAM is using this code or these programs as a learning material. So students can be engaging with these materials, they can be using them, tinkering with them, that they're actually involved in creating, using this programming medium as a new way to explore. In the history of science education, there's been a huge emphasis on inquiry and having students really engaging with materials and evidence. I think that coding is another form of material and another form of evidence that they should be interacting with as they're learning. And then finally, I think programming and coding give a lot of opportunity to make these experiences more personally meaningful. I think this plays a lot into the arts, like you can make this kind of learning your own. You don't have to just learn something from somebody else, you can kind of make it something that's interesting to you. So those are sort of the elements that I'm trying to access when I talk about CCSTEAM. And lately I've gotten really into the P5.js editor. And there's a few reasons that I think, particularly for maybe 7th through 12th grade, and a lot of this I'm thinking about the middle school and high school learning experience, but I think you can extend it beyond that with different platforms and different ways of looking. I really like P5 because it has an incredibly low floor. I've seen students get onto it really fast, be able to play around with things. It's just on the web, so you don't, a lot of challenges happen when you try to install stuff on your computer and you interact with the hardware. It can create a lot of challenges, so you can get right on it. Because it's on the web, even if you only have a Chromebook or a tablet or something, you can get onto the P5 editor, and it's visually powerful and it can do a lot. It's the language of the web. So you sometimes run into issues around speed. So you have to, if you're using a compiled language, you're going to be able to do things faster. But for 90% of the things that you're doing, or maybe more, it just lets you do a lot that's visually powerful. So I really like this platform, and that's sort of what I've been exploring in some of this work with creative coding for STEAM. So that's sort of the context of what I'm talking about, and in a second I want to kind of show you how I've used it and the type of collaborations, but are there any questions or comments up to this point? Yes?
What school in Brooklyn?
It's called Packer Collegiate.
Yeah.
Yeah, it's on Gerolman Street. But again, I've done, some of these projects are particular that are coming up are going to be projects I use there. But I've also done some work with various, like at STEM Teachers NYC, they work with a lot of public school teachers as well. There's a lot of opportunities to do this kind of work. And what I think is powerful about it is that with minimal class time, you can get students involved in some of this at various different levels. And they can engage in the type of thinking. And I think that'll come across more with the examples. But are there any other comments or questions before I show some examples? So the first example I'm going to show, this was an evolution sketch that I created. And if you go on to the presentation, there's a link to the sketch. So in fact, some of you might not have a device, so I will go onto the sketch with you. Here is the sketch. You can kind of see, are people, raise your hand if you're familiar with the P5 web editor platform. Okay, so if you can, I would suggest going onto this. In fact, I'm gonna give you a minute. If you can, like, look on with someone. Like, the first thing I did with this was the way I talked with a biology teacher. So this is a biology class. They were like, let's set something up. Let's put some circles on the screen. We found this graphic for an eagle, and you can move it around with the mouse. We'll talk a little bit about the coding of this. But the first question that we ask the students is are these circles evolving? Are they evolving? And in fact, let's play around here. Like, what are some things you're noticing as I'm moving this circle around here? And if you want, you can look at the code, but you could also just look at the eagle here. Let's see here. Oh, there's a lot more screen real estate when you plug into the monitor. I think this is good. Just got a few more of these here. Okay, let's see. Oh, interesting. Okay, so what do people think? Do you think these circles are evolving? Any thoughts here? Like, did anyone notice anything going on in this? Like, what was going on there?
As you move the eagle over the circle, they got darker.
They got darker, okay. So how did you know they got darker?
Well, I was following one circle and then just moved the eagle over it and it changed colors.
Okay.
And I kept doing that over and over.
Does anybody have a guess of what? Like, what do you think is going on the right-hand side of the screen here? I don't know if it's easy to see from the back.
Is this sort of supposed to simulate like a faux ecosystem? Like there's like a hierarchy depending on the colors, and then the eagle feeds off of a specific level of creature.
Yeah.
So they're like grouping into like their designated classes. I don't know.
Yeah, well, but what is, like, I was just moving it sort of randomly around the screen.
Well,
So why would it be going after certain colors?
I noticed it was only going after the whites.
Interesting. So this was something that we presented with the students, and they had the opportunity to get on their computers and try it out. And this actually isn't the simplest code that example, but I think it's really easy to get on board with. In some ways, it's more like the computer aided instruction, because I just created this simulation. What the students noticed, and if you look on the right hand side, is that over time they got darker. And so then we started to notice like what's going on here. And in fact, it's not that they're turning darker. Whenever I go over one, it disappears. And then sometimes you can notice that a new one appears. And we can actually look, let's see, do I have the right code up here? If you look here, there's certain functions here, like there's an eat function. So the eat function, if I go over one of the circles, I think the kids started calling them mice, because they decided the eagle must be hunting mice. But if it goes over a mouse or one of the mice, it disappears, and that's the eat function. If there's not enough mice on the screen, which in biology they call the carrying capacity of the ecosystem, then it makes a new one, and that's the reproduce function. But what's interesting about the reproduce function, which sort of came out of the discussion that we started to have, is that it chooses one of the circles that's on the screen and it copies it. So based on what's left on the screen, you see change over time in the traits of these circles. And so in fact, they are sort of getting darker. At 0, the average shade was 118, and by 50, it got to 109. It didn't get lower at 100, but if we kept doing this, eventually they'd get darker. And what the students determined was that the reason I'm hunting the white circles is because I can see them, right? The screen is black. And so there's actually some circles on the screen that you can't see at all because they have a shade in P5 of 0, which is pure black. And so you can't actually see them. Now I might randomly hit them as I'm going around the screen, but you can't actually see them on the screen. So that was sort of some of the interesting discussion that happened as we were using this. But that isn't even really what I'm talking about with creative coding for STEAM, because this is just, like, I don't know if you've ever been to the PhET website. They have a series of like computational simulations for various science topics that you can try out. But I wanted the students to kind of get involved in interacting with the sketch.
The what website?
It's called PhET, P-H-E-T. That's through the University of, it might be the University of Colorado. P-H-E-T. But they have a lot of simulations as well, but you can't tinker with the simulation. So what we did in this class is, after doing a lot of exploration of this, we asked the students, well, can you change, like, we had some discussion, is this actually evolution? Like, you can have whole conversations about what are the components of evolution. And they had had some discussions about this in their biology class. But then you can wonder, well, can I change evolution? Can I change the course of evolution? And that's where we started to play around with the sketch. Let me see here if I could do this. So if I go in here, if you look at the draw function, I'm setting the background to 0. So you can, if you're on a computer right now, you could go in here and you could duplicate this sketch and make your own copy of it. But I encourage you, like, what if I changed the background to 255, which is white?
So wait, how did you get to that?
It's linked on here, this link here.
Wait, how did you get that? How did you get that, do we have the PowerPoint somewhere?
Yes, it's this tiny URL here. It's
Oh.
CCSTEAM PCD.
I do not know how I missed that, sorry.
No problem. Yeah, I put it on whiteboard at the beginning because always people say, can you go back to the first slide? And
That's PCD, right?
PCD. So if you go to this sketch, does anybody have it, like, how do you think it'll change the course of evolution to make the background white?
I think it'll do the like inverse, with where before the black circles were the most evolved, and because they could evade like the quote unquote predator, and now the white circles will be the most evolved.
Yeah, and the kids could do that. Like, it's pretty easy to change the background, and they weren't expert coders, like they had done maybe a couple of days of looking at this, but just that simple change, you can start to see, like, does it actually change the course of evolution? Is evolution changing? Some kids said, wait a second, I wanna, like, what would happen if, because in class they were talking about speciation, where like there's divergence and you get two different species. Like, what if I made a rect that was from 0, 0 to width divided by 2, height. So what if I made half the screen black and half the screen white? Let's see, fill 0. Like, what would happen there? And then they started to have whole conversations, like usually when a species divides, there has to be some sort of boundary. But you can still kind of follow, like, is this going to cause a split? Like, maybe all the ones in the middle are going to start to disappear, and the pure white and the pure blacks are going to have an advantage, and there will be a split.
You just answered my question.
Okay, so, but we don't know. Like, what's great about this is we don't know what the outcome's going to be, and to be honest, this is actually how biology works. Like, all of biology and all of evolution is just a big simulation. There's just real living organisms that are participating in that simulation. And here, like, this isn't an exact representation of what's going on, but it's like close enough that you can start to think about the meaning of those things, and you can have these deep conversations. And the assignment that they got was to like see what kind of ways they could change it. So one thing you could change is this kind of what biologists call the selection criteria. We can have different types of selection. We could also change the variation. So it doesn't have to be the shade of the circle that's important. What if I had some of the circles moving faster and some moving slower? The way that I scaffolded this for the students is if you look in here, there's this thing called sketch that has all the simplest stuff that's in the sketch. Some students want to go nuts and they want to try out different things. So there's another JavaScript file called helper.js, which has the more complicated stuff. Like, that's how I got them all moving around randomly. But if you go in there, you could make a trait that some of them move faster than others. In fact, one thing that was easier for the students to do is they made the size of the circle the trait. And the size of the circle drove the selection like 10 times faster than the shade of the circle, because you couldn't get the small circles. Like, they were too small to hit with the mouse pointer, and so they saw, like, when there was really strong selection, it drives it much faster. And so you could kind of see how this whole biology thing works, and it just led to these really interesting conversations. Some of them played with the inheritance. So literally, you can go to this. Here, I'll go back to the sketch. Here, if you look at reproduce, right, it finds a child shade here on line 10, and then it creates a new disk of that shade. You could just make it, what if the children were random? What if all the offspring shades were just random and had nothing to do with the population that was there? That would break evolution. Like, if the traits of the children don't depend on the population that's there, it will never change the average shade. And so they could kind of explore this. And the other thing that's fun is it's both like this really deep scientific conversation, but it's also like a visually powerful conversation. Like, you could add color in here. You could play around with the aesthetics of it and kind of mix. I think that's where the STEAM element really gets exciting, is you're having this deep biology conversation, but you're also thinking, like, what kind of effect do I want to create in my sketch that's going to create something interesting? One student decided they wanted to see what competing selection looks like, and so they made it that, I think they left the screen black, but they made it that the closer you are to pure black as a shade of a circle, the less likely the reproduction is going to work. And so the student was able to kind of break evolution by making the counter selection exactly equal to the selection of the eagle, so that it just stayed at the same average shade over time. So those are just some things. You can keep playing with this and see what you can come up with. But I really like this idea that it leads to deep discussion, and it made them kind of think about like what's really going on with evolution and what are the essential elements. Like often in biology class you'll get this list like evolution depends on selection, variation, inheritance, time, but what does all that mean? Here you can kind of explore what it means.
I changed it so that it only eats the mice, I guess, when you click.
Okay.
And it actually changes it a lot.
Okay, how is it different?
Because it's faster now. Because think about when it just hovering is enough and it eats more black.
But randomly without realizing.
Yeah, but when you have to actually click for it to work, then.
Nice. Yeah, and that's what's exciting is you can get this idea in your head like, oh, what's going to happen in this case? I can make this better than the thing I gave you. And I like that. Like you should be able to make it better than the original thing I gave you because you can kind of explore your own ideas.
I was going to make a one with all the colored dots, but it's hardwired for shade.
Yes. I mean, you would have to come up, right now, there's a trait that's from 0 to 250 that I think I have 6 like different levels of it. So we'd have to come up with some way to do that. Some changes are going to be more complicated to do, like from a programming standpoint, and some are going to be easy. And actually, I kind of like that aspect of the lesson. The student had to figure out what they were interested in, but also what they were capable of testing. And so sometimes they might have an idea, I want to play with color, and then they're like, I'm not ready to play with color because it's too baked into the way it was set up. I'm going to try something else. But then as you keep on playing with it, you're able to access different parts as you get more comfortable with the code. Any other questions about the evolution sketch or comments? This is a really favorite one of mine.
I noticed there's no mutation.
There's no mutation, and some of the kids played with adding mutation, and like how much mutation is, like the amount of mutation in real evolution is tiny. It's really small. Like they were putting in huge mutations. It made the biology teacher a little bit uncomfortable. She was like, that's a lot of mutation. But it's like, but you play around and you realize like ultimately you're trying to model something that's out there.
I feel like in like our biology there is a lot of mutation, but it's stretched over such a long period of time, so it's harder to see.
Yes.
Whereas this, you can control the speed or the timeline of the mutation.
Yeah, over a long period of time there is,
Mhm.
but in this time scale, it's very little because it's like DNA has gotten really good at copying itself.
Mhm.
Yeah.
How do you confront bias? Because an eagle is going to eat a mouse because it's hungry, not because it's brown or white. So how do you confront bias in terms of people just clicking the white ones because they're the brightest?
Yeah. That's something that the students talked a lot about. That they felt like it wasn't, so there's the bias of making a decision to take it,
Right.
Versus like it being something that's like unconscious. And even if it's unconscious, it could have bias. So it was something that we talked about in it, and some students tried to come up with ways like, how can I do this in such a way that there wouldn't be bias? But we didn't fully solve that problem. And some of them talked about, well, maybe I could make like an AI component to the eagle, where it's following a set of rules, and maybe it's like looking for ones that have a certain, like based on the color scheme. One of the places where the bias seemed much less pronounced was in the size. Because in the size, you could just move it randomly and you'd be less likely to hit those small ones. And it didn't feel like it was as controlled by bias. But I noticed that some groups, like the rate at which it drove down was really high, and then you could have that conversation in class, like, why is it that this group, the selection pressure is so high? There's some bias in there. So it opens it up, but it is hard to quantify. I think that's a great question. Okay, so another project that we did, here we go, and I have some of the things that I talked about on this slide, but it's called, I called a motion sketch. So this was, let's see if this is working here. So this was, I've done this in a 6th grade class, and I've also done this in a high school physics class. But the idea here is they make these buggies. Here, let me I'm going to make a small change to the code before I explain what I'm doing. You'll see here there's a place where it says to adjust the x position. So I'm going to say x equals x plus 5 here. So this is changing the position of x for the buggy over time in the draw loop. And I'll talk a little bit about that, but it just makes it so we'll see more. So, oh wow, that's a big change there. I have to think about that. Okay, so, what am I doing here? Oh yes. So in this case, the students were using these buggies, and they make these buggies that move at a constant speed. So one of the questions that came up in the class was just like, how fast are these buggies moving? How are you going to characterize that speed? And they had to come up with, and this is sort of the unplugged part of the activity where they're just thinking like, what do I need to measure? What does speed even mean? But what I liked about bringing it to the computer is once they're starting to think about what speed means, what does it mean on the computer? And one of the things that's really powerful when studying motion in an animation context is it gives you huge insight into the motion. And one of the reasons is in most high school physics classes, they have 2 parts of the teaching of motion. You talk about constant motion, and you do all this algebra with like a constantly moving thing. And then you have a whole conversation about accelerating motion. But in P5, it's all the same thing. Like it's all about updating position, and later you can update velocity, but you can model any kind of motion in here. And it's very simple. Like I can just simply go, let's see, I can change this number here, and I encourage you to get onto this sketch. Here we go. And you can play around with like what's happening to the motion of this object. And so what I've done here in this sketch is I've just changed the x value, and it's moving across the screen here. Oh, I see what happens here. I think somehow in this I made delta t smaller here. Wait. Yes, okay. So this was supposed to be like this. That's what it's supposed to be. Okay. Nice. Okay. So what I did was, in fact, in the original sketch, I think I was playing around with it last night, so I made it a little harder for you. There's this variable called delta t, which tells you how big the time step is. And it makes it jump from one to the next. And then here on line 32 is when you're updating the position of, you're updating the position of the x position of the buggy. And so it allowed for all these conversations in the class. Like one of the things the kids wanted to do was make the buggy move more smooth. So they changed delta t here to a smaller time step. Like say you made it 1/4 of a second that you wanted it to be the time step. Now it's it's less choppy in some ways, but you've made the speed 4 times as great. And so you can start to think like, why is it going faster just because I have a smaller time step? But it's because if you look down here, you're increasing by an x value this, like you're increasing by the same x value no matter what the time step is. So that leads you to this idea that the increase, the change in x should actually be the velocity times the time step, and not just a fixed value. And later you can even add in things like you can take this velocity variable and you can make that, let's see here, if you do v equals b plus 1 and x equals x plus v times delta t, you can start to play around with accelerating motion. We should see some, yep, there you go. So just by changing this velocity in every frame, we can start to get all different kinds of motion. And you can even work up to periodic motion. Like we could have a spring, if we bring in Hooke's law, we can do all kinds of different things with that. I think I saw a hand up
Yeah.
in the back.
My buggy's not even moving.
Yeah, did you put in x equals x plus 5?
Where was that?
Down here on line 32. So if your buggy doesn't move until you change the x value. And again, like there's some complicated things in here, like I put in a graph and I put in, like you could make these simpler or more complicated depending on what your learning objectives are. But the idea is that you can start at a low floor and do very simple things, but then you can do very kind of complicated things. And the last thing that I'll show, because we're running out of time, is I did one called, has anyone heard of Pick's theorem? So Pick's theorem is this thing they teach in geometry at my school. I think it's in a lot of geometry classes. If you count the number of interior points and you count the number of boundary points, and this is like a lattice of points, you can figure out the area of any polygon. And there's like a rule, it's like some formula. And we could play with this and we could come up with what that rule might be, and we could do that in an inquiry way. But what was interesting to me is when we started doing this work with it, I realized from a coding perspective, it didn't really matter what Pick's theorem was to me. What I cared with was, how do you know if a point is interior or on the boundary? And you can have this whole investigation of like, if I know those 3 vertices, how do I know which points are inside the shape and which points are on the boundary of the shape? And it became this whole new mathematical investigation. Like if I'm going to write this program, I need to think about the math in a very different way than the teacher was teaching Pick's theorem just on paper. And so we had a whole discussion about the equation of the line and whether it was on the line. And we even came up with this idea of like, which side of the inequality is it on? And it all kind of worked out. But then we ran into a problem when we had polygons, because we couldn't use the side of the inequality purely. So again, like I think creative coding for STEAM lets you access different kinds of thinking. It lets you get deeper into certain kinds of thinking. But it also lets students kind of control the means of production to kind of push their learning forward. And so that's why I'm excited about this work. Feel free to contact me if you have other questions. There's some other sketches in here on the presentation. And also I write some of these things on Medium. So thank you very much.